Okay guys, so let's talk about indefinite differentiation. Sorry, that's not the right word. Indefinite integrals. And hopefully this video will be pretty short, and hopefully my dog doesn't bark in the middle of it. So let's see how it goes. Okay, so far every time we've taken an integral, we've had bounds on it. So like from a to b of f of x dx, and we say that physically that represents the area under the curve from a to b of f of x, right? That's what it represents, this area here, okay? However, as you also know, in order to find this area, we take the antiderivative, and then we plug in our endpoints a to b, right? Which is what the fundamental theorem of calculus says, right? The fundamental theorem of calculus says that the integral from a to b of f of x dx is equal to its antiderivative of b minus the antiderivative at a. Now, when we deal with indefinite integrals, we don't have bounds, okay? The integrals we've been working with are definite integrals because you have a definite answer, okay? Like you have an exact answer. This is what it is, okay? An indefinite integral doesn't have bounds, so your answer is less precise. So before we start looking at indefinite integrals, let's re-explore, or let's look at again, the derivative. So let's take the derivative of d dx of x squared plus 3x plus 4. So when I take that derivative, I'd end up with 2x plus 3, right? And I know that my constant, the derivative of my constant, is really a 0, but who writes plus 0, right? Now, what's going to happen when we take our indefinite integral is we're going to have to account for the fact that the derivative of a constant is 0, okay? So again, like if I looked at a similar function, so a similar quadratic, so x squared plus 3x plus 12, that would give me the derivative of 2x plus 3. So in this case, my derivatives match, right? 2x plus 3, 2x plus 3, but my functions are different. And the indefinite integral accounts for that constant, okay? So we're going to look at indefinite integrals today, and then next class we'll look at U substitution, and then we're going to look at solving indefinite integrals with an initial value. Okay, that'll be after your next assessment. So this is what we're going to do. So we're going to look at an integral, and again, it's not going to have any bounds. So let's slide this up. So this is your first example, example 1. Okay, so we are going to integrate x squared plus 3 dx. Okay, now we're going to integrate it the exact same way we were doing before. Bella, come! The exact same way we were doing before, using the antiderivative. However, since we don't have any bounds, we're not going to plug anything into the antiderivative. Okay, so let's just go piece by piece. So we're going to first look at x squared. So as always, I'm going to add 1 to my exponent and divide. So that's going to be x cubed over 3. And then we haven't even really looked at the antiderivative of a constant because we've been using our constant rule when we've been looking, when we've been taking the definite integral, right? But hopefully you know that to end up with a constant, you'd have that number in front of x, right? The derivative of 3x gets you back to 3, just like we showed you up here. And then we have to account for the fact that we could have some constant, right? Like in this problem up here, we had a 12. So because we don't know what that constant is, I know this is really fancy, but you put a plus and a capital C, okay? I don't really know the, like, make sure your C looks like a capital C. I know lowercase and capital C's look the same, but it needs to be capital C, so just make sure it's obvious, okay? Now, hopefully you should then look at your answer, which is what we have here, and say, okay, I need to simplify this to look pretty. So in front of x, you always have your invisible 1, so this really is 1/3 x cubed plus 3x plus c, and that would be your final answer, okay? It is, because you don't get functions that look like this, right? You want to simplify it. That's a function you're used to kind of seeing, okay? So get rid of your fractions and use reciprocals instead, okay, or fractions instead. Okay, let's look at another example. Okay, I want to integrate secant squared of x dx. Okay, so again, I need to take the antiderivative. So what function gives me a derivative of secant squared? Well, tangent squared. It's not tangent squared, just tangent of x. And again, you could have had a constant, right? It could have been your original functions hypothetically could have been like tangent of x plus 7. You don't know. You have to always account for the fact that you have that constant. I know it seems silly, but without this plus c, your answer is wrong. So keep it, use it, don't get rid of it, okay? It's really, really, really important. You need the plus c. You need to account for a constant. That's why when you guys kept saying the derivative or the integral is the antiderivative, I kept saying not really. It's a piece of it, right? This is the antiderivative piece. This is the constant piece. You need both, okay? Again, if you look at that last example, yeah, we used our antiderivative here. Why isn't it drawing? Like, this is our antiderivative, but we're just assuming that we have some constant. Okay, we're assuming we have some c value. That c could be 0. That c could be 27. Okay, we're not really getting back to the original function. To do that, you need an initial condition, and we're going to deal with that later. Okay, so for now, take the antiderivative and add your constant. It's really, 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 really important. Okay, we'll look next class at figuring out how to find the constant, and then we're going to look at u substitution, and then you'll have a test. Not next week, but the week after. Okay, if you have any questions, I'm happy to answer them.